So there's this train, and the train moves at a steady rate of 75 miles an hour from 7 a.m. to 9 a.m. How far does it travel? We've heard this before. We've looked at it algebraically. This is the line y equals 75 on a graph of velocity with respect to time. This is the 2-hour time frame. And we said, well, 75 miles an hour, and you do it for 2 hours, you should go 150 miles, right? And so we look at now finding the area. I'm going to call it the integrate. We're integrating under this curve, y equals 75 from the interval 7 to 9. And if we find the area, we use that area model. This is 2. This is 75, and we can use this area model to get that 150 miles is how far the train went. The area under the curve of velocity gives a net change of position in that 2-hour time frame we were looking at. That's what we're going to do today, and our homework is going to have some of this on that too. It's called integrating geometrically. Do you notice that I didn't need a calculator to find the area under this curve? Because it's a rectangle and that's geometric. And that's kind of what we're going to look at in this section. So integrating geometrically, you don't need your calculator. You don't necessarily need to set up an integral. Now, we easily could have set up an integral. I'm going to sum up an infinite number of rectangles, which is silly because I only need one because it's geometric, but we could do this from 7 to 9, and the curve we're integrating under was y equals 75. So it's a pretty simplistic one, but you could set that up. And if you put this in your calculator, and I really do encourage you to do that right now, use your Math 9, you're going to get 150. Okay. And so geometrically or with your calculator can help you out. Summing up in infinite rectangles on the interval 7, 9, under the curve y equals 75, and we can get the same thing. Okay, but we're going to look at geometric this time. So let's go ahead and take a peek at this. I'm going to go ahead and draw this, and that's your homework. It says, and on your submissions, please make sure that you really are drawing these, because that's what we're looking at, is that you clearly have done these geometrically. So we'll go from the interval -3 to 4. The curve is y equals 3. And I don't think that's going to be too hard for us to go ahead and find the area on that interval. I'm getting 7 times 3. 7 is the width times 3 is the height. And so 21 units squared would be this area. Okay, let's try another one. Well, let's just use the same drawing, and you tell me what the answer is. Look at these. They look like they should be, it's the same curve, but we're integrating from 4 back to -3. That should give us just the opposite result. So the key on this geometric isn't that you're just finding the area, but that you're keeping in mind you're finding the signed area. So you probably won't be too hard to find areas geometrically, but signing them is where Mr. Childers and I really want you to start thinking. All right, so we'll look at this one. And pi is just, well, it's going to look very much like the other one. Y is going to equal 3.14-ish instead. And we can find this area. And I'm getting that the area would be 4 base times the height, which is pi. And I'm going to stop at 4 pi and take a quick look to see if it should be signed positive or negative. Integrating left to right, I'm going with positive. Curves above the x-axis, the area is above the x-axis. All right, let's try this one. This one, kids usually have to think about a bit, and in class, I just let you suffer. But because I'm on a time restraint here, and so are you, I'm sure, this comes from the equation, right? And that's a circle with the center at the origin, 0, 0, and the radius. Remember, this is r squared, so our radius would be 2. So we should know that equation of a circle. And then what we've done is just solved it for y. I'm going to subtract the x squared, and then I'm going to square root. And it's only the positive one. I don't see a plus or minus here, so it's not the area of a circle. It's just the area of a top half of a circle with radius 2. So I'm going to draw that. center, and if this is geometry, if we're struggling right now, okay, this is definitely a geometrical thing. So we're centered at 0, 0. I know my HK stuff. And we're going to go 2 this way, 2 this way, 2 this way, as our radius is 2. And I'm going to draw probably world's worst semicircle. There. And it says we're going to integrate from -2 to 2. So it just wants that top half of that. And we do know that the area of a circle is pi r squared. And so our area should be half that. So I'm getting 2 pi as the integral value here, the signed area. And I'm going with positive because we're going left to right. The area that we've drawn is above the x-axis. Okay, so this one probably is not going to be as a huge stretchy stretch here. We're just going to go ahead and draw basically the same shape, except it wants the bottom half of our circle this time. But it looks like we're still integrating from -2 to 2. So we're going left to right, but the area is underneath. So the area isn't going to change, but the signed part of it will, because we're below the x-axis. Okay, folks, that's all I have for you on that.